Right. Now I think so. You can hear me speaking, right? Right. I will discuss today. Now today I will do some more time. I think today I will discuss some more time. That's important because somehow we have to finish this chapter as much as possible. So I will do it maximum time today. Right. Mm, then mm, give me 1 minute. Right. Right. Now I think last day we started to discuss this transverse waves. Due to some connection issues, I think we were not able to discuss remaining section. Now today, so we'll try maximum to cover this longitudinal waves and transverse wave section, right? Then somehow I need to finish this properties of waves also. We are starting this today. We'll do our best, right? Now, when we're talking about transverse waves, now, if I briefly explain what we learned last day. Now we know that waves. Basically, I explained that waves means propagation of energy, because wave carries energy from one point to another point. Then I explained that now how this energy is transferred. Let's say now this point is point capital A, this point is point capital B, right? Then energy is to be transferred from point capital A to point capital B. Then we know that energy transfer occurs as a wave. Wave is carried that energy from point capital A to point capital B. Now, somehow, this energy must be propagated through the medium. Now, energy at point capital A must be propagated to point capital B through the medium. Then we know that energy is propagated as a wave. The first of all, you should understand what does it mean by a wave. That's very important. Wave means a disturbance occurring in the medium. Always understand wave means, always you understand wave means disturbance occurring in the medium. Disturbance. Disturbance in the medium. It can be a solid medium. For an example, when you consider propagation of water waves, disturbance occurring in the water, right? If not, when you consider sound waves, when sound waves are propagating in the air, that disturbance is occurring in the air. When sound waves propagating through a solid metal rods. In that case, disturbance occurring in that metal rods. So therefore, simply wave means some sort of disturbance occurring in the medium. Disturbance in the medium. Disturbance in the medium. So that's what we defined as waves. Simply wave means what? Disturbance occurring in the medium when energy transfers from one point to another point. That's the idea. Then I discussed that now. We divide these waves into different categories, right? So we can categorize all the waves into two categories now. Now there are three categories. We can divide into mechanical waves and electromagnetic waves. We will discuss them later. Then we can divide these waves into transverse waves and longitudinal waves. If not, we can divide standing waves and propagating waves. But right now we are learning about transverse waves and longitudinal. Then after we finish learning Doppler effect, we will learn about standing waves and longitudinal standing waves and propagating waves. And then we will learn that mechanical and electromagnetic waves, right? Then I told you that what does now when we come to these longitudinal waves and transverse waves, then we learn that what is this transverse waves. Now we can categorize waves into transverse waves and longitudinal waves. Transverse waves. The next type of wave is longitudinal waves. Longitudinal waves. Now, what does it mean by transverse waves? What does it mean by longitudinal waves? A transverse wave means direction of noise. I told you that when energy propagates, we know when energy propagates from point A to point capital B, medium particles get disturbed. Basically, medium particles they vibrate. When energy is carried from energy transfers from point capital A to point capital B, medium particles get disturbed. That means medium particles are vibrating. Transverse waves, I explained that if the vibration of the medium particles, let's say now in between point A and point B, there are air particles. When sound wave propagating from point capital A to point capital B, now sound wave propagating from point capital A to point capital B. Direction of wave propagation, if not direction of energy transformation occurring horizontal right direction, right? Direction of wave propagation is horizontal right direction, right? Right? This is wave propagation. Direction of wave propagation. Direction of wave propagation. Do you understand? Now, what is transverse waves? If the wave propagates, if energy transfers horizontal right side direction, if the medium particles vibrate perpendicular to the wave propagation. Medium particles vibrate perpendicular to the wave propagation. That type of wave we are calling as transverse wave. Transverse wave. These medium particles vibrate perpendicular to wave propagation. We call that type of wave as transverse wave, right? Then I think I discussed only there. So then I could not discuss remaining section. Then we stopped, right? Right. So then, right. Okay. Right. 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 Okay. Now I'm explaining all these things about transverse waves. Okay. Now draw this diagram together with me. Draw this diagram together with me. now I'm drawing a transverse wave, right? If I draw a wave, now just think about now this transverse wave is formed when we vibrate a stretched rope, right? At a particular instant, when t equals 0, when t equals 0, this is the how this is how wave appears, right? Right? Okay. So then now very carefully listen. Now my rope was horizontal. Now I'm talking about transverse wave produced on a stretched rope. Initially my rope was horizontal. This time, who is my medium particles? My medium particles are rope particles because this wave is propagating through the rope. In that case, our medium particles are rope particles. So initially, I will mark location of few rope particles. When the rope was horizontal, I will mark few locations of rope particles, right? So this particle is point capital A, point capital B. This particle is point capital A. This particle is point capital A, right? So exactly, I said this particle is point capital A. Initially, my rope particle in the horizontal line, when the rope is horizontal, capital A is one of the rope particles, capital E, right? Then this is my capital B particle. This is my capital B particle, capital B, capital B particle. This will be my capital C particle. This will be my capital C particle. This is my capital C particle. My capital D particle. Capital D particle. So draw this diagram with me. Capital D particle. Capital E particle. Capital E particle. Capital E particle. Right. Capital E particle. Then we'll mark capital E particle and yes, capital E particle. We'll mark this particle is capital F. This particle is capital F. This particle is capital F. Right. So I will mark this particle. Look at here now. A, B, C, D, E, F. Right. This particle is capital G. This particle is capital H. Right. So I say this particle is capital I particle. Capital I. Right. Now you should understand. Now these transverse waves continuously propagating from one point to other point. Let's say this transverse wave propagates to the right side direction. This wave is propagating to the right side direction, right? Direction of wave propagation. This transverse wave is propagating to the right side direction. That means energy is propagating to the right side direction. Direction of wave propagation. This section is completely theory, right? Complete theory. So therefore, very carefully listen. Direction of wave propagation. Wave propagation. Direction of wave propagation. Propagation. Then we can clearly see that now it's a transverse wave. The medium particles vibrate perpendicular to the direction of wave propagation. Wave is propagating horizontal right direction. The medium particles must vibrate perpendicular direction. That means in vertical direction. Medium particles vibrate. That means they move up and down. Now, when the rope was horizontal, medium particles on the rope A, B, C, D, E, F, G, H, I all were in horizontal locations. Now, when the wave is propagating, when I freeze at a particular instant, let's say when t equals 0, I freeze the wave, then this is how my rope would appear. In that case, what happened to capital A medium particle, which was in horizontal when the rope was horizontal? Now capital A medium particle, capital A rope particle has shifted exactly maximum displacement. Just think about each medium particle in vertical motion. This capital A medium particle has shifted the maximum possible displacement. Now here is my capital A medium particle, right? I mark capital A dash. Then what happened to capital B medium particle? Capital B medium particle shifted vertically, but comparing with displacement of capital A particle, displacement made by capital B particle is somewhat less. Am I correct? Displacement, vertical displacement made by capital medium particle is somewhat less, P dash, B dash. Then capital C particle has displaced in negative direction. A and B vertically upward direction they displaced. Capital C, capital D and capital E vertically downwards they displaced. Then this one is C dash. When we consider capital D particle has the maximum negative displacement. Am I correct? D dash, E dash, E dash, F is at there is no displacement for capital F particle. See, now initially when the rope was horizontal, then also capital F particle was at this point. Even at this particular instant in the wave propagation, then also capital F particle is exactly the same point. Then we can say that there is no displacement of capital F medium particle. That's very important. That's very important. It's very important, right? In that case now, capital G will be here, G dash, capital H will be here, H dash, H dash, right? So then we need to understand now in transverse waves, now you can clearly understand there are some instant now in when transverse wave propagates, every instant, now we can clearly say that location of medium particles are different. Am I correct? Now very carefully listen. When transverse wave propagates, what would happen for the medium particles? The displacement done by each medium particle is different. Am I correct? Just think about medium particle A. It has done a maximum positive displacement. Capital B medium particle has done positive but less displacement comparing with capital A. C particle displaced negatively. Then we can clearly see that when transverse wave propagates at a particular instant, displacement done by all the medium particles are different. Then we introduce two main names, crest and trough. Generally, what does it mean by crest? Generally, what does it mean by trough? Crest means the location where the crest means it's something this way. We can define this way. Crest means the particle obtain maximum displacement. The maximum displacement point. That's what we call as crest. Now look at here. When you consider capital A, the capital A particle has displaced maximum positive direction. Therefore, we call maximum positive displacement points. Maximum positive displacement points, we call them as crest. Very carefully listen. Maximum positive displacement points, we call them as crest. This is crest. Right? Maximum positive displacement point, we call them as crest. These are crest. Maximum negative displacement points. Just think about the displacement of capital D displaced negatively with the maximum displacement. Then we are calling this point as trough. This point is called as trough. Right. Now what would happen now when now? Do you think now when wave propagates now? This wave is continuously propagating forward direction. Then at this particular instant, cresta belongs to A point and H particle. Cresta belong to capital A and capital H particles. Trough belongs to capital D particle. Do you think throughout the wave propagation, always crest will be at point capital A and point capital H? No. The next instant, crest will be obtained by capital B. If not, trough will be obtained by capital E. At a particular instant, now in this particular instant, crests and trough belongs to A, H and D particles. Did you understand? If I draw, now this wave is propagating. If I draw when the time is t equals 1 second, if not the next instant, the wave propagation, if I draw the next instant wave pattern, this wave is moving forward direction. Now I will draw the next wave, I will draw, right? When t equals 0, now this is the wave. This wave must be propagating forward direction at the time. After small time later, if I draw the wave pattern, my wave pattern would be in this way. Because wave must be propagating forward direction. Right. Then my wave would be this way. Right. Am I correct? This must be my next instance wave pattern. So you also draw together with me. Very carefully draw it, right? If you don't carefully draw this wave pattern, sometimes we can't exactly know the location. Right. Okay. Now this red color wave is the wave belongs to next instant when t equals delta t. When the time is t equals delta t, then the wave pattern would be this way when t equals delta t. Now in that case, in this case, just think now, when t equals 0, capital A medium particle was at the maximum displacement, that means at the crest. When t equals 0, capital D medium particle was at the maximum negative displacement, that means trough. Then what happens? I told you continuously these medium particles, they don't move with the wave propagation. These medium particles vibrate perpendicularly continuously. Now what happened? The next instant, what happened to capital A dash medium particle? When t equals 0, capital A dash medium particle was at here. The next instant, when the time is delta t, what happened to capital A dash medium particle? Capital A dash medium particle has moved downward direction. When wave is propagating forward direction, in the next instant, capital A dash medium particle has propagated downward direction. See, to this location. What happened to capital B dash medium particle? Capital B dash medium particle has shifted upward direction. Capital B dash medium particle is moved in upward direction. Capital capital B dash medium particle is moved in upward direction. See, this medium particle has moved in upward direction. Upward. You can't clearly see. It's moving in upward direction. B dash. Then what happened to C dash? That is also moving in upward direction. Now it will be somewhere here. What happened to capital D? Capital D medium particle is also moved upward direction. Capital E dash medium particle has moved downward direction. Am I correct? Then what happened to capital F? When t equals 0, capital F medium particle was at 0 displacement. Now capital F medium particle has moved downward direction. What about capital G? Shifted upward direction. You understand? Sorry, shifted downward direction. Then I think you can understand. Shifted downward direction. Shifted upward direction. Then you can understand. Now, very carefully listen. Now, I take so much time and I explain this concept because there's a reason. Because in MCQs, they can ask very tricky MCQs. Because they are asking some sentences and they ask whether this sentence is right or wrong. In order to clarify, in order to understand that statement is right or wrong, you should have a deep understanding about motion of each medium particle. Do you understand? The summary is what? When wave propagates, if it is a transverse wave, medium particles vibrate perpendicular to the direction of wave propagation. In this case, wave is propagating right side direction. Medium particles, each medium particle vibrate perpendicular direction. At a particular instant, that means if you freeze the wave, at a particular instant, if you freeze the wave, location of each medium particle is different. At the particular instant, some medium particles at the maximum positive displacement. Some medium particles are at the maximum negative displacement. Some medium particles has zero displacement, right? Then we call medium particles at the maximum displacement, that location, maximum positive displacement, we call as crest. Medium particles at maximum negative displacement, we call them as trough. These points I think you can remember, you can understand. Now, if you need to draw the location of medium particles, the next instant, then wave is propagating forward direction. You have to draw a wave has propagated forward direction, and based on that, you can decide the direction of medium particles in the next instant. Right? I think you can understand what I explained. I think you drew this diagram. Right? They will write down. I'll ask one question now. Now I'll ask one question. If you can answer, put in the chat box. Now it's very clear that these medium particles vibrate. What can you say about motion of each medium particle? Now we learned almost linear motion, and we learned circular motion, rotational motion, and before this lesson we learned simple harmonic motion. Then if I ask you that, what can you say about the motion of medium particles? Which type of motion they follow, they obey? Any reply? These medium particles are moving in simple harmonic motion. So therefore red color pen important. Important. After you did this diagram nicely, important, important. Each medium particle moves in a simple harmonic motion. Each medium particle moves in a simple harmonic motion. Right? People. Right? Next point. Next point. Okay, then we'll come to the motion of each medium particle. Now I'll ask that. Now in simple harmonic motion, we learned that. Just think about vertical simple harmonic motion. In vertical simple harmonic motion, this is our equilibrium point. Equilibrium point. Now this is our positive amplitude. This will be our negative amplitude. Let's assume in that way. Now there's a particle. That particle moves in a vertical simple harmonic motion. Vertical simple harmonic motion. When the particle is at the positive or negative amplitude, when the particle is at positive or negative amplitude, what can you say about the velocity of the particle? We learned in simple harmonic motion, when particle is at the amplitude velocity is zero, when the particle is at the equilibrium point, velocity is maximum. Am I correct? Velocity is maximum. At the amplitude, velocity is zero. Velocity is zero. Then you can clearly understand. Now I mentioned each particle A, B, C, D, E, F, G, H, I. All the medium particles moving vertical simple harmonic motion. Now, just think about when t equals 0 instant. I'm talking about when t equals 0 instant. When t equals 0, capital A particle is at the amplitude because maximum positive displacement means amplitude. Capital A particle is at the amplitude. Capital D particle is at the negative amplitude. Capital H particle is again at the positive amplitude. Then what can we say about the velocities of A, D, and H? Velocity of medium particles at A, D, and H. They are at instantaneous zero velocity. For a small instant, at that particular instant, medium particle A, D, and H, their velocities are zero. Red color point important here. Red color point important right on here. Write down. Capital A, comma, capital D, and capital H. Here, capital A, comma, capital D, and capital H. Particles are at instantaneous rest. Particles are at instantaneous rest, and and now just think about when you consider this black color wave, capital F, particle is at the equilibrium point. Then we know velocity of the particle at the equilibrium point is maximum. Then capital F particle at this instant, its velocity is maximum. And capital F is at its maximum velocity. Capital F particle is at its maximum velocity, right? Capital F particle is at its maximum velocity. Then now we have defined what is this crest and what is this trough. Subtopic crest. Subtopic crest, write down this way. Now you have to highlight that previous sentence, highlight that instantaneous rest, highlight that one. Then now I told you what is crest and what is trough. I already explained. Write down crest, write down the highest point of a transverse wave. The highest point of a transverse wave. The next point, it represents the point where the particle of the medium have maximum positive displacement in the upward direction. It represents the point where the particle of the medium have maximum positive displacement in upward direction. Highlight maximum positive displacement upward direction. Highlight maximum positive displacement upward direction. Highlight them. Highlight. Then subtopic trough. Subtopic trough. Write down. Trough is the lowest point of a transverse wave. Trough is the lowest point of a transverse wave. Next point. It represents the point where the particle of the medium have the maximum negative displacement in downward direction. The maximum negative displacement in downward direction. Maximum negative displacement in downward direction. Now I'll ask one question. Now we know that when this transverse wave propagates to forward direction, what would happen for the crests and troughs? Reply. When transverse wave propagating forward direction, what would happen for the crests and trough? Right? Look at this. When this transverse wave propagates in forward direction, what happened to the crest? Initially when t equals 0, here was our crest. When t equals delta t, here is my crest. And then what happened to the crests? This crest has shifted forward direction. Then when t equals 0, here was our trough. Now here is my trough. What happened to the trough? With the propagation of the wave, troughs also propagated forward direction. Crest is propagating forward direction. And then what we can say, always this crests and troughs, they also propagate in the direction of wave propagation. Red color pen important. Red color pen important. When transverse wave propagates, comma, crests and troughs also propagate. Crests and troughs also propagate in forward direction. Crests and troughs also propagate in forward direction. But medium particles only vibrate, if not oscillate. But medium particles only oscillate vertically up and down. But medium particles only oscillate vertically up and down. Right. So then, write down next point. The direction of oscillation of medium particles. The direction of oscillation of medium particles can be determined as shown in the figure above. Can be determined as shown in the figure above. As shown in the figure above. By marking the position of string. By marking the position of string That means by marking the position of the wave, okay? By marking the position of the string, after a few moment, after a few moment, with a dash line. But here I didn't mark a dash line, I marked what? Full line. After a few moments with a dash line. Do you understand now? In order to understand now, it says that now if you want to decide the next location of the medium particles and direction of the medium particles, what you should do, draw the wave pattern in the next instant. Then you can clearly identify the location of each medium particles. That's the idea. Now raise your hands. Up to now, everything is very clear. Raise your hands. Up to now, everything is very clear. All right. Mm, right. 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 Now, very important thing. Okay, now before going to this longitudinal waves, one more important thing is in MCQs they might ask that they might have they will give a wave like this and they will mark few points in the wave like A, B, C, D, E. And what they ask, select the medium particles. Select the medium particles which have same phase. Now already we know that in simple harmonic motion, I think we learned what does it mean by a phase. We know that idea. We have that idea. Now, how do we find the medium particles which have same phase? So how we identify medium particles which have opposite phase? That's very important. Write down now. Important. This is very very important point. Take your super red color pen. Take your super red color pen and write down this idea. If medium particles have, if medium particles have same displacement and velocity. Now understand displacement and velocity. They are vectors. Right? Then vectors means not only their magnitude must be same, but also their direction must be same. Right? Write down. If medium particles have same displacement and velocity, comma, these medium particles are in same phase. Those medium particles are in same phase. Highlight same displacement and velocity. Same displacement and velocity, same phase. Highlight same displacement and velocity, same phase. Now look at here. Now just think about, now we know that exactly point capital A. Look at here. Exactly point capital A. Medium particle. Just think about when t equals 0, this wave. Exactly point capital A. Very careful. Exactly point capital A. A medium particle was at instantaneous rest. A medium particle was at instantaneous rest. Then the next instant it will go down. That's the meaning of this. Exactly at point capital A medium particle at instantaneous rest, in the next instant it will go down. When you consider capital D medium particle, capital D medium particle, when the time is t equals 0, capital D medium particle is at instantaneous rest. In the next instant, it will go upward direction. Then when you consider capital H medium particle, that is also instantaneous rest at this instant. In the next instant, capital H medium particle will go down. Right? Then what can we say about capital A medium particle and capital H medium particle? Raise your hands, how many of you say that capital A medium particle and capital H medium particle are in same phase? Raise your hands, how many of you say capital A medium particle and capital H medium particle are in same phase? Now, what is the condition now? The condition is if both of them have same displacement. Yeah, obviously, capital A and capital H medium particles, both of them have same maximum displacement, same displacement. That's correct. Velocities are zero. Their velocity is also zero. So therefore, we can say that capital A and capital H are in same phase. Capital A and capital H are in same phase. Same phase. Now we'll consider another two medium particles. We'll consider another two medium particles. Just think about capital B medium particle. Just think about capital B medium particle. Sorry. We'll take capital B medium particle. This capital B medium particle. Capital B medium particle, and we'll consider uh okay, I will draw a separate diagram. If I erase, it will take time. Okay, erase it. It's not clear. In this case. Right. Now, where is my capital A? It's my capital A particle. It is my capital B particle. Let's say this is my capital K. This particle is capital K. This particle is capital L. Right. Now, capital A. Let's say this particle is KL. I see this particle is AM. Now we know that capital A and capital M particles are in same phase. The capital A and capital M particles are in same phase. Now, do you think capital B particle and capital K particle are in same phase? It seems like displacement of capital B particle, displacement of capital B particle, and the displacement of capital K particle, they are equal. Not only their displacement must be same, but also their velocity. Velocity in the sense magnitude and direction also must be same. What can you say about the velocity? At this instant, capital B is moving in upward direction, but capital K moves in downward direction. And then we can clearly say that capital B and capital K, they are in opposite phase. Capital B and capital K are in opposite phase, not same phase. But what can you say about capital B and capital L? Capital L is also moving in upward direction. And then we can say that capital B and capital L, they are in same phase. Capital B and capital L are in same phase. I think you guys understood. Now let's just take a screenshot if you don't have enough time to write down. This is the idea. So then, whatever we learned regarding longitudinal waves, if I summarize again, look at it. Now then we will go to transverse waves. Whatever we learned regarding transverse waves, if you summarize it, then what we learned? We know the basic understanding about transverse wave, direction of wave propagation in medium particles vibrate perpendicular to the direction of wave propagation. That type of wave we call as transverse waves. We know that idea. When you consider vibration of each medium particle, they move in simple harmonic motion. That's very important thing. Then, when that wave propagates, let's say in the forward direction, every medium particle at a particular instant, when that wave propagates in forward direction at a particular instant, displacement of each medium particle is different. There are some medium particles at maximum positive displacement. There are some medium particles at maximum negative displacement. Some medium particles are at zero displacement. Then we named crest means the points where maximum displacement, positive displacement occurs, we named them as crest. The point where maximum negative displacement occur, we named them as trough. Right? That's the important thing. You understand? Right? Then we learned about this phase, how to find the medium particles under same phase. how to find medium particles on the opposite phase. Now you can understand. And this section is entirely completed. Now we'll start about longitudinal waves. Your main topic, longitudinal waves. Now main topic, longitudinal waves. Right. Now we'll write down this way, longitudinal waves. Write down a wave in which particles of the medium, now it's completely opposite to the transverse waves. Now in transverse waves, medium particles vibrate perpendicular to the wave propagation. In longitudinal waves, medium particles vibrate in the direction of wave propagation. If your wave is propagating forward direction, medium particles also vibrate in forward direction, back and forth, forward, backwards. Write down a wave in which portion of the medium, a wave in which the particles of the medium, okay, a wave in which the particles of the medium, a wave in which the particles of the medium through which the wave is traveling, through which the wave is traveling, move back and forth, move back and forth in the same direction as the wave propagates. Move back and forth in the same direction as the wave propagates. Right? The next point, write down. Next point. The oscillation of the medium particles are, the oscillation of the medium particles are parallel to the parallel to the direction in which the wave is moving. The oscillation of the medium particles are parallel to the direction in which the wave is moving, the wave is propagating. So then we draw this diagram. This diagram. Now, now these are your medium particles, okay? Right. Now your medium particles. Now I see direction of wave propagation is horizontally right side direction. Direction of wave propagation. Direction of direction of wave propagation. Wave propagation. Propagation. Then medium particles vibrate back and forth. Medium particles oscillate in the direction of wave propagation. That is parallel to the wave propagation. Wave is propagating horizontally right. So therefore, medium particles also vibrate horizontally forward and backward, back and forth. Draw this diagram. Direction of medium particle vibration. Direction of Vibrations of medium particle. Oscillation. Oscillation of medium particles. Then if you completed that diagram, right, quickly. Quickly write down, quickly. It's a very important idea. Now still I didn't teach you what is mechanical waves, right? I didn't teach you yet, okay? But normally understand longitudinal waves. When it comes to longitudinal waves, all the longitudinal waves are mechanical waves. Still you don't know what is mechanical waves. I will explain later. Now write down important point. All the longitudinal waves are mechanical waves. All the longitudinal waves are mechanical waves. Right? Highlight mechanical waves, longitudinal waves. Highlight them. The examples of longitudinal waves. Examples. Number one. Now example of longitudinal waves. Number one. The most popular longitudinal wave is sound waves. Number one, sound wave. Because mostly we explain all the concepts in longitudinal waves by considering sound waves, right? Number one, sound wave. Number two, compression waves in spring. Compression waves in spring. Number three, number two, compression waves in spring. Number three, seismic P waves. Now, you don't understand what does it mean. Seismic, SCISMIC, seismic, capital P waves. Seismic P waves. This will be also taught in upcoming chapters, right? Then write down the way of propagation of sound waves. Write down the way of propagation of sound waves. The way of propagation of sound waves by producing compression and rarefactions. The way of propagation of sound waves by producing compressions and rarefactions when striking a tuning fork. When striking a tuning fork. Now, I think still you don't know what is this tuning fork, but don't worry, I will explain. The way of propagation of sound waves by producing compressions and rarefactions when striking a tuning fork. Now, I told you that the most popular example for longitudinal waves is sound waves. So therefore, we explain all the characteristics of longitudinal waves considering sound waves. Now, tuning fork means that is some sort of device which can vibrate medium particles. For an example, look at it. I think you know what is tuning fork. Basically, tuning fork means it is having two prongs. The tuning fork is having basically two prongs. Right. Now, what happens when you strike the tuning fork? This tuning fork. Now, when you strike the tuning fork, that means when you beat, I don't know what to say exactly. Now, some sort of it contains two prongs, and when you strike to the wall or when you strike to a wood block or whatever, what will happen? These prongs start to vibrate. Just take a ruler. When you take a ruler when you strike to something, what will happen? This ruler will vibrate. Very similar manner, when you strike tuning fork with the wood block or something else, what would happen? These prongs start to vibrate this way. Sometimes you can't see its vibration. Its vibration is very high. Then what happens? Just think what would happen now. We know that the surrounding is, if we strike the tuning fork, these strong start to vibrate, right? Start to vibrate, right? So when this tuning fork prongs vibrate, what would happen for the medium particles? Now, air particles are surrounded by this tuning fork. Air particles are surrounded by the tuning fork. Then what would happen to these air particles? What would happen to these air particles? Now, initially just assume that these air particles in the atmosphere have spread uniformly, but that's not possible. But we have to assume in that way. Just think that these air particles have spread in the surrounding uniformly. That means the gap between two adjacent air particles is always same. That's how we have to assume, right? Then what would happen? What would happen? Now I will show a video, right? Because it's very difficult to explain what's happening exactly. Now these air particles, these dots represent air particles. Initially, they have spread uniformly. Just before vibrating the tuning fork, surrounding air particles have spread uniformly. They're having same gap, right? Right. Uniformly. Okay, uniformly they have spread. If I draw some lines, I'll draw some lines, then I'll erase it. Right. Now, initially, air particles in the atmosphere have spread uniformly. That means the gap between adjacent air particles is always constant. But what would happen with the vibration of tuning fork? With the vibration of tuning fork, what would happen? The location of these air particles changes. Now draw this diagram with me. Draw this diagram with me. I will show a video also. Can I understand? These medium particles have equal gaps. Right. Now I will show a video. Then you can easily understand in that case. Right? Give me a second. Mm, right. Give me a minute. Right. Now just think about now. We know these speakers. Now, if you carefully observe vibration of a speaker, what happens when speaker vibrates? Generally, what happens? The air particles. Look at it. Now, even it is tuning fork. Now we can replace instead of tuning fork. Just think about a speaker. Even when speaker is vibrating, what would happen? Then when this tuning fork is also vibrating, what would happen for the medium particles? Medium particles also disturbed by the vibration of the tuning fork. Medium particles adjacent to the tuning fork also get disturbed due to the vibration of the tuning fork. So therefore, what would happen when the tuning fork vibrates? The adjacent medium particles also start to vibrate under same frequency. You understand? When adjacent medium particles start to vibrate, what would happen? Due to the collision with the adjacent medium particles, the adjacent medium particles also start to vibrate. Do you understand? Now let's say now, initially due to the vibration of tuning fork, these red color medium particles also start to vibrate back and forth. So when these red color medium particles vibrate, they will collide with adjacent medium particles. When they collide with adjacent medium particles, they also start to vibrate. Then when these medium particles start to vibrate, adjacent, these medium particles start to vibrate back and forth. Then these medium particles also vibrating back and forth. So likewise, what happens? The produced now, energy produced here, the energy transfers from the tuning fork to somewhere here by vibrating, by disturbing the medium particles. Do you understand? Do you understand very carefully? Very carefully listen. Now, when this tuning fork is vibrated, energy of this tuning fork is propagated from tuning fork to a place somewhere here by vibrating the medium particles. Initially, vibration with the tuning fork, the adjacent medium particles vibrate, they collide with adjacent medium particles, they also vibrate. Due to this continuous collision, all the medium particles move back and forth, then wave is propagating forward direction. If energy is propagating forward direction. But if I draw, if I need, if I show a video, if I show a video, if I show a video, look at here. Now I will share my screen. Now, if you can see the screen, just let me know. Uh, Right, give me a minute. I think I'm not able to share the screen. Okay, that's a problem. Okay, now I'm not able to share the screen, but I will send the video clearly. Then you are able to see them. Now, then what happens? Now you understood all the medium particles, they vibrate back and forth. Now you know all the medium particles, they vibrate back and forth. You know why? Due to the continuous collision, all the medium particles vibrate back and forth. As a result, what happens? When transverse wave propagating, we know that there are some crest and troughs formed. Some particles were at the maximum positive displacement every instant. Some particles were at maximum negative displacement. Then every instant there are crests and troughs formed. With the time, what will happen for the crests and troughs? They are changing. Crests and troughs, they are propagating forward direction. Very similar manner, due to the continuous vibration of these medium particles, what will happen? There will be some regions. Now, initially, I told that initially, just before vibrating the medium particles, I'm talking about longitudinal waves. Just before vibrating the medium particles, I told you that the medium particles have spread evenly, uniformly. The gap between the medium particles was same. Due to the vibration of the tuning fork, what would happen? The medium particles also vibrate, medium particles also go back and forth. As a result, what will happen? Just think about a particular instant you could identify that there are some regions, medium particles come very closer. You can identify there are some regions, medium particles have came very close. And there are some regions, medium particles have spread well. Some regions, medium particles compressed. Some regions, there are medium particles well distributed. Well distributed, right? In that case, what happens? You can identify some regions, medium particles came closer. Some regions, medium particles distributed well. Look at it as a vibration. Now, as this medium particle, just think about these medium particles move forward direction. You could observe that. Now, if these medium particles move forward direction, you could observe some regions, medium particles came together. If these medium particles move backward during the back and forth vibration, just think these medium particles move backwards. Right. Okay. Then what happened? Just think about now. Now, if I draw properly, right? Now, while I am drawing the diagram, you also do the diagram. Okay, it's very important. Now, these medium particles move forward direction. Just think these medium particles are at instantaneous rest. These medium particles move backward direction. Right. And just think these medium particles are instantaneous rest. These medium particles move backward direction. And just think these medium particles are instantaneous rest. These medium particles are move forward direction. Then you can understand. Then you can understand. Let's look at it. Then you can understand. You can understand at a particular instant when you freeze the wave at a particular instant, you will understand. You will understand. Now these medium particles have went backward direction. Then you will be able to understand these medium particles moved forward direction. So in this lesson, there is no much questions, but you should understand all the concepts properly. If I draw further some medium particles, so you also draw with me. In that case, now these medium particles are under stationary instantaneous rest. Instantaneous rest. Let's say these medium particles move forward direction and these medium particles move backward direction. In that case, you will be able to understand in this particular region, medium particles get closer. Medium particles get closer. Medium particles get closer. Then you will be able to nicely identify when longitudinal waves propagate. For an example, when we vibrate the tuning fork, sound wave propagates through the air particles. When this sound wave is propagating through the air particles, what would happen? Initially, these air particles were distributed evenly. As this wave propagates, due to the disturbance of the medium particles, some regions medium particles come close. Some regions medium particles spread more away. Some regions medium particles come closer. Right? So we are calling the region where medium particles came close. They as we call as compression. Compression. So like a crest in transverse waves, crest. Now what happened to these medium particles? These medium particles are at maximum displacement. We call them as crest. Sorry, compressions. There are some regions medium particles have well distributed, well spread. We are calling them as rarefactions. Rarefactions. Draw this diagram. Rarefaction. Rarefaction. This is compression. 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 Then what can you see now? Comparing with the normal gap now, when there is no wave propagation, comparing with the normal gap between the medium particles, in compression, the gap is very low between the medium particles. Comparing with the normal situation, the gap between the medium particle is very high in rarefaction. When these air particles come closer, what can you say about the pressure in this region? Pressure in this region is very high. What can you now? Let's say the pressure in the normal region is capital P. Then what can you say if I say pressure at a compression is PC? The pressure at rarefaction I say PR. Comparing with the normal atmospheric pressure, if it is a compression, pressure is very high in this region. Comparing with atmospheric pressure, what can you say about the pressure in rarefaction? That is low. You understand? And with the wave propagation, what would happen for these compressions and rarefaction? In transverse wave, when transverse wave is propagating forward direction, we know that crests and troughs also propagated forward direction. Then like in this longitudinal waves also, when the wave propagates forward direction, this compression and rarefaction is also moving forward direction. Now at this particular instant, there's a compression here. But the next instant, exactly there's a rarefaction. Here compression. There rarefaction. So therefore understand when this wave is propagating, this compression and rarefaction also propagate in the wave propagation direction. Now raise your hands. Up to now, everything is very clear. If you understood, raise your hands. Okay, now draw this diagram quickly. Write this diagram. Now we use this dotted technique. This is the right way of explaining longitudinal waves. Right way of explaining longitudinal waves. Right. Now we'll write down. We'll write down. We'll write. Now we understood what's happening in longitudinal waves. Right. We'll write down topic compression. Compression. Now write down under compression. Write down. Compression is the region. Compression is the region of a longitudinal wave. Of a longitudinal wave where the particles of the medium are where the particles of the medium are pushed closer together. Where particles of the medium are pushed closer together, resulting increase in pressure and density, because we know that when air particles come closer, what would happen to the pressure? Now in that region, air particles are well packed. If the air particles are more packed in a confined region, pressure is very high. What can we say about the density? Density means mass per unit volume. Within that confined volume, if more particles are packed, there is more mass in that confined volume. If there is more mass in confined volume, what can we say about the density? Density is also high. So therefore write down resulting an increase in pressure and density. Highlight compression pushed closer together. Compression closer together. Increase pressure density. Highlight compression closer together. Increase pressure density. Now next point, generally in longitudinal waves, the compression. Now generally in longitudinal waves, the compression seems like, acts like a crest in the transverse waves. Do you understand? Therefore write on next point. It is typically represented as the crest of a wave. It is typically represented as the crest of a wave. Right? Then subtopic rarefaction. Subtopic rarefaction. Write down. Write down. Rarefaction is the region of a longitudinal wave. Rarefaction is the region of a longitudinal wave where the particles of the medium where the particles of the medium rarefaction is the region of a longitudinal wave where the particles of the medium are pushed where the particles of the medium are spread more away where the particles of the medium are spread more away, resulting a decrease in pressure and density, resulting a decrease in pressure and density. The next point you can understand, right? Then generally these rearfractions in longitudinal waves we consider as the troughs in a wave. Next point, it is typically represented as the it is typically represented as the trough of a wave. Trough of a wave, right? Then I think now we discussed about longitudinal waves and transverse waves. That's the idea. That's the idea. Now I could show some videos, but still I'm not able to show them because not because of the now it's not now okay, there is some technical issue. Not now you might think that it's now if host can access that the host is not either both of my accounts. Host is someone else. Okay, that's the problem. Therefore I can't have the access right now. Okay, now subtopic wavelength. Subtopic wavelength. Now we can define wavelength in many waves. Now by considering transverse waves we can define the wavelength. If not by considering a longitudinal wave, and we can define the wavelength. Now coming upcoming sections we will learn about wave fronts. By considering wave fronts also we can define the wavelength. So therefore put your topic wavelength inside the bracket lambda. Now I told you this lesson is entirely theory, so we can't do questions, entirely theory. The topic wavelength inside the bracket lambda. Wavelength inside the bracket lambda. Now you know how to write lambda, right? Lambda. Wavelength lambda. Notation is lambda, right? Then there are plenty of definitions. Write down first definition. Distance between two consecutive points. That's very important. Write down. Distance between two consecutive points that are in same phase. Distance between two consecutive points that are in same phase with each other. With each other is defined as wavelength. Look at it. Just look at this one. Now I explain considering a transverse wave. If I consider transverse wave, right? Right. The transverse wave. So then I will mark few points. Point capital A, B, C, D, E, F, G. Point capital A. This is point capital A. Point capital B. Point capital C. Point capital D. Point capital E. Point capital F. Point capital G. So you also draw with me. Now you know that how to decide which particles are in same phase and which particles are in opposite phase. Now you are able to define. Now which particles are in same phase. Now how wavelength is defined. Now please highlight in the previous that definition. Now definition is distance between two consecutive points. Distance between two consecutive points in same phase, right? You should highlight. It's very important. Two consecutive points. Distance two consecutive points, very important, not just 2 points. It must be two consecutive points. Then highlight same face. Distance, two consecutive points, same face, highlight them. Now tell me, now there are few points, point A, B, C, point capital D, point capital E, F and G. Right now, how do we identify which points are under same face? Now, do you think, just think about point capital B. Now, we know that point capital B and point capital F, they are the crests, right? If it's a transverse wave, we know that point capital B and point capital F, they are the crest. Point capital D is a trough. It's a trough. Trough. Point capital B and point capital F, those are crest. It's a crest. And then already I told you that point capital B, point capital F, they are adjacent. They are adjacent. Right? Point B and F are two consecutive points on the same face. Because we know that B and F, they are crest. So obviously they should be on the same face. Point capital B and F are in same face. But if we want to define wavelength, wavelength means distance between 2 points on the same face. That's wrong. Wavelength means distance between two consecutive points on the same face. Right? That's the very important thing. For your understanding, I will draw one more wave pulse. Then only you will understand. Right. Now GH, I say this is point capital I, J, K, L. Now look at it now. Capital B, capital F, capital K, they are in same phase. That's true. Now just think about point capital B and point capital F. They are in same phase. Point capital B and point capital K, they also in same phase. But wavelength is defined the distance between two consecutive points on the same phase. Wavelength means the distance between two consecutive, two adjacent points in same phase. So can we can the point capital B and point capital K, they are in same phase, but they are not adjacent one. Adjacent of capital B is capital F, not the capital K. B and K, they are in same phase, but B and K are not adjacent particles in same phase. Adjacent particles for capital B in same phase is capital F. Understand that important thing. Now D and I, they are trough. Capital D and capital I are adjacent particles in same phase. So therefore, gap between them must be equal to wavelength. Draw this diagram. What about point capital A and point capital E? A, point capital A, E, G, L. They are in same phase. If I mark B, F, K in same phase. In same phase. Same phase. But understand B and F, adjacent. Adjacent of B is F. Adjacent of F can be either B, if not either K. The gap between F and K, that is wavelength. F and K are in same phase and they are adjacent. So therefore gap between them is wavelength. Now what can I say about capital A and capital E? Capital A and capital E same phase. Capital G same phase. Capital A, capital E and capital J, they are in same phase. Very important things. Now, do you think capital A and capital C in same phase? Capital A and capital C in opposite phase. Capital A and capital C opposite phase. Opposite. Capital B and capital D opposite phase. Capital B and capital D opposite. Right? Capital E and capital G opposite. You understand? The A, E, G, L same phase. Ni? A, E, J, A, J, A, E, J, same phase. C, G, C, G, and L same phase. C, G, and L, they are in same phase. Right? So likewise, you can write down D and I same phase. D and I same phase. Then you can define your wavelength. This is lambda. This is lambda. Now I think you guys understand what I explained. Right? You guys understand. Then we can tell now the right definition for a wavelength is the distance between two adjacent or two consecutive points on the same phase, that is we call as wavelength. Based on that definition, we can define wavelength further. How? The distance between two consecutive crests as the wavelength. The distance between two consecutive troughs as the wavelength. Write down the distance between two successive, if not two consecutive, the distance between two successive crests inside the bracket or troughs. The distance between two successive crests inside the bracket or troughs, close the bracket, of the wave is defined as wavelength. Of the wave is defined as wavelength. Of the wave is defined as wavelength. Right? Right. The next definition, then we can say now. Now, when we consider longitudinal waves now, okay, draw this diagram again now. If you draw a rough diagram again, now wavelength lambda, wavelength lambda. If you want, you can draw it. We can define by considering longitudinal waves also. We can define the wavelength. Now, how we defined wavelength using crests and troughs? The distance between two consecutive crests, if not distance between two consecutive troughs on the same phase. Now, no need to mention same phase because obviously crests and troughs are in same phase. The distance between two consecutive is important. The distance between two consecutive crests, if not distance between two consecutive troughs in are we call as wavelength. Now, what about if we define wavelength considering longitudinal waves? Then we can write down the distance between two consecutive compression inside the bracket or rare fractions. Close the bracket. The distance between two consecutive compressions inside the bracket or rare fractions. Close the bracket. Is defined as wavelength. Is defined as wavelength. Right? In that case, now look at it. Look at here. Do this diagram with me. Then we know this region is compression, this region is rarefaction. Compression. We know this region is rarefaction. This region is rarefaction. A compression. Rarefaction. Then how we can define the wavelength considering compression and rarefactions? The distance between two consecutive compressions is we call as wavelength. Distance between two consecutive compressions. Two consecutive compressions. See, this is wavelength. If not distance between two consecutive rarefactions. Distance between two consecutive rarefaction is we call as wavelength. Right, this diagram. Right, okay. So then after you wrote this, we'll take a 10-minute break. Then we'll start again. We'll take a 10-minute break and we'll start it again. Okay. Now I will start again at 10 a.m. I will start at 10 a.m. I will start at 10 a.m. Right. 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 Can you hear me? Right. We'll continue again. So we'll continue again. Then we define wavelength by considering what compressions, fractions, and crests and troughs. There is one more definition for wavelength. We'll write them by considering wave fronts. I didn't explain what is wave front, but we will learn today as soon as possible. Now we can define wavelength in another way also. Write down wavelength. Write down the distance between two consecutive wave fronts. The distance between two consecutive wave fronts in same phase is also defined as wavelength. Distance between two consecutive wave fronts in same phase is also defined as wavelength. Right. Right. Okay. So then we discussed about what is wavelength. So what is the unit of wavelength? Lambda. Write down. Unit of wavelength is lambda. Dimensions of wavelength, capital L. Sorry, my bad. Units of wavelength is measured in meters, some sort of length. Units of wavelength is meters. Dimensions of wavelength, that is a capital L. That is capital L. That is capital L. Right. It is measured in meters. Dimension of wavelength lambda. So that must be capital L. Capital L. Right. Then subtopic wave frequency. Now we know what is wavelength. Now subtopic is wave frequency. Inside the bracket, simple if. Wave frequency. Wave frequency. Simple if. Right. Then write down. Now idea is very simple. Within 1 second, how many oscillations occur? In simple harmonic motion, we learned what is frequency. Number of oscillations within 1 second per unit time. When you consider 1 second, how many number of oscillations occur, we call it as wave frequency. Write down the number of complete cycles. Same idea. Number of complete cycles or oscillations that occur in unit time, that occur in 1 second. Number of complete cycles or oscillations that occur in unit time is called as wavelength. Then what is the is called as the frequency, wave frequency, my bad, is called as the wave frequency. Then what is the unit of wave frequency? Hertz. Unit is hertz. We measured in hertz. Now you know hertz means per second, right? Per second is we call as hertz. To respect scientist hertz. So what are the dimensions of wave frequency? Dimensions of wave frequency. Per second means what are the dimension of per second? T minus 1. T minus 1. Right. Then subtopic time period of wave. Time period of wave inside the bracket capital T. Time period of wave inside the bracket capital T. Time period capital T. Then always understand there is some sort of relationship between wave frequency and time period. Frequency and time period. Now, how we define frequency? Frequency means number of oscillations, if not number of cycles within 1 second. Within 1 second, how many number of cycles are made? So what is time period? Time taken for one cycle. Time taken for one oscillation. Write down time period. Write down. The time taken for one complete cycle or oscillation is called as time period. Time taken for one complete cycle or oscillation is called time period. Then you understand the relationship between time period and frequency now. What is the unit of time period? Seconds. Unit seconds. What is the dimension of time period? Now, dimension of time period is also capital T. Now, this case dimension and symbol of time period seem same, but capital T represents this capital T symbol represents time period. Its dimension is also capital T. Then what is the relationship between time period and frequency? We can write down time period equals 1 over simple if. Always understand in rotational motion, circular motion, and simple harmonic motion. Always understand time period equals 1 over frequency. If not, frequency equals 1 over time period. That's important equation. Write down this one as well. This one. Right. Then subtopic wave speed inside the bracket capital V. Subtopic wave speed inside the bracket capital V. Wave speed inside the bracket capital V. Right. Write down the definition. Distance traveled by the wave perpendicular. Distance traveled by the wave per unit time is wave speed. Distance traveled by the wave per unit time is wave speed. Wave speed capital V. Now, how do we obtain a relationship between wave speed, frequency, and wavelength? How do you obtain relationship between wave speed, frequency, and wavelength? I think almost you guys know that V equals F lambda equation. But you should understand how this V equals F lambda equation came. That's very important. How this V equals F lambda equation come, that's very, very important. Right? Now, what is now? When one cycle completes, now when one oscillation completes, what is the distance traveled? One cycle means lambda wavelength. Wavelength, one cycle means understand. Look at it. One cycle means understand. One cycle means one complete oscillation. Right? Lambda. So this is one cycle. This is we call as one cycle. This is lambda. One cycle. When one cycle completes, distance traveled is lambda. Right? The number of cycles formed by the wave within 1 second. Number of cycles formed. Now, it is mentioned that number of cycles formed. Number of cycles formed. Now, what's my goal? I'm going to build the relationship between V, F, and lambda. That's my goal. Now, it has given number of cycles formed within 1 second. Within 1 second. In 1 second. Now, what is this number of cycles per 1 second? What is this frequency? Simple if. Simple if. Every 1 second, simple if number of cycles occur. Distance of one cycle is lambda. Then what is the distance traveled by the wave? What is the distance traveled by the wave when there are simple f number of cycles every 1 second. Within 1 second, what is the distance traveled by the wave? Lambda into f. When one cycle travels, lambda distance has traveled. When wave travels simple f number of cycles, distance traveled by the wave is simple f into lambda. Am I correct? The length of one cycle is lambda. Length of one cycle is lambda. Length of one cycle. Length of one cycle. That is lambda. So therefore, we can say that distance traveled by the wave within 1 second. We can say distance traveled by the wave. Therefore, we can say distance traveled by the wave in 1 second equals when one cycle completes lambda distance covered, when simple f number of cycles covered means distance traveled by the wave is f lambda. Then what we call distance in 1 second, distance per unit time. This is what we call as velocity, not speed. Then this is we call as what? Speed. Therefore, we can write down V equals f lambda. Speed equals f lambda equation. Write down these things quickly. And put a point important. V equals f lambda equation can be applied. Write down. Important. V equals f lambda equation can be applied to any wave in the universe. Any wave in the universe. Can be applied to any wave in the universe. Then that section is done. Now, let's say now there are some important points related to V equals f lambda equation. Now, why we use V equals f lambda equation? When wave is propagating in a medium, it can be a water wave propagating on the surface of water, it can be sound wave propagating in the air, if it can be a transverse wave propagating in the rope, we can apply V equals f lambda equation for any type of wave, right? Now, some people think that in this way, some students think that the speed of the wave in a particular medium, let's say velocity of sound in the air. Now, when sound waves propagate through the air, velocity of sound waves. Do you think velocity of sound wave changes with the wavelength of frequency? Now, I have a sound speaker. I have a speaker because sound waves propagate from the speaker. I have a speaker. If I change the frequency of the speaker, very carefully listen. If I change the frequency of the speaker, do you think velocity of the sound wave propagating in the air changes? Do you think velocity of the sound wave propagating through the air will change? No, right? No. It seems like V equals F lambda equation according to some people. Some people argue that according to V equals F lambda equation, when F changes, V must be changed. Always understand in a wave, when wave in a particular medium, when a wave in a particular medium do not change its velocity. Always velocity of a medium, always velocity of a wave in a given medium is always a constant. Velocity of a wave in a given medium is always a constant. There are some conditions it changes, but generally understand velocity of a wave in a given medium is always a constant. What would happen when the frequency increases? Relatively, when frequency increases relatively, what would happen? In order to maintain same velocity, wavelength decreases. Did you understand? When frequency increases, relatively wavelength decreases and it maintains same v velocity. So therefore, red color pen write down. The wave speed in a medium is independent of the wavelength inside the bracket lambda, close the bracket, and frequency inside the bracket, simple left, close the bracket. The wave speed in a medium is independent of wavelength lambda and frequency, simple left. Then you can clearly understand when frequency of a wave increases, what would happen to the wavelength? Decreases. Some sort of inverse relationship between frequency and wavelength. When frequency increases, wavelength decreases. Write down, red color pen. There is an inverse relationship between frequency and wavelength. There is an inverse relationship between frequency and wavelength. Right. Then everything I explained. Now put your topic. Now we are going to plot some graphs. Variation of wavelength with frequency of a wave in a particular medium. Variation of wavelength with frequency of a wave in a particular medium. Now, if your y-axis represents lambda and if your x-axis represents frequency, how would you draw the graph? Look at it. Now, you have to plot the graph. Now, we know v equals f lambda equation. We know v equals f lambda equation. Now, your y-axis represents wavelength, your x-axis represents frequency in that case. Lambda x-axis, right? Frequency simple. If you draw the graph, how would be the graph? Then we know that equation. We know popular equation v equals f lambda. V equals f lambda. Then my y-axis is lambda, and if I subject lambda, lambda equals v dot 1 over simple f. Then you can clearly understand there is some sort of inverse relationship between lambda and frequency. Then how would we draw the graph? Lambda and frequency graph, how would we draw the graph? Lambda is inversely proportional to the frequency. In that case, how we do the graph? The graph would be this way. Now again draw the graph. Now this time your x-axis is not frequency, but your x-axis is 1 over f. In that case, how would be the graph? Now your x-axis is 1 over f. Now your x-axis is 1 over f. 1 over f. 1 over f. Then how would be the graph? Then lambda equals v 1 over f. My lambda represents y, right? 1 over f, that is my x-axis. X equals, this is some sort of gradient, y equals mx graph, right? I think we discussed that section also, right? Right. So then we'll discuss about this idea of wave pulse. Write down idea of wave pulse. Topic is wave pulse. Now you should understand what is wave pulse. Write down a short non-periodic wave front. A short non-periodic wave formed by a single input of energy formed by a single input of energy rather than a continuous or repeated input energy. Write down. A short non-periodic wave formed by a single input of energy rather than a continuous or repeated input energy. A wave pulse now. It's very easy idea, right? Now what is wave pulse? Now just think about rope. Will try to form transverse waves on a rope. So this end is fixed, right? Then is fixed. Now what would happen? Just take about this end of the string. If I continuously vibrate, if I continuously vibrate the string, if not the rope, up and down, then what would happen? Continuously wave is propagating forward direction. When I continuously vibrate the rope up and down, wave is continuously propagating in forward direction. Right. Continuously. Right. Now, rather than continuously vibrating, if I vibrate the rope only once, just think now I am holding the rope from my right hand. Now, what I do, now that rope is well tight, well stretched, other end is connected to a fixed end. What I am doing, I just only vibrate the rope only once, only one up and down. So if I vibrate the rope only one up and down, then what type of wave will be appearing in the rope? There will be a wave front. So there will be a wave front like this. Then if I vibrate only once, then you can identify if I vibrate only up and down, then there will be a wave front you can observe. There will be a wave front propagating forward direction. So this is we call as wave front. When we continuously vibrate, there will be full wave. If we only one time propagate up and down, if we only one time vibrate up and down the rope, there will be a wave front, right? So then wave fronts can have different shapes. It's not compulsory to have this shape. There are different shapes of wave fronts. They have different geometries. Then this type of wave front is possible, right? This is one possible wave front. Rules diagrams. If not, there can be a wave front in this way. There can be a wave front in this way. This is also the kind of wave front. The wave fronts can be any shapes. Then there can be a wave front in this way. Right. There are different shapes of wave fronts. I can draw many shapes. I think you understood the idea, right? Yes. Keep drawing. Give me a second. Right. Now, sorry, this is what we call as wave pulse. Okay, wave pulse. Now you guys understood now what does it mean by a wave pulse. Now I think previously I explained using the word front, but it must be pulse. A pulse, a one pulse. Now put your topic wave fronts. Now put your topic wave fronts. Write down, write down, write down. Geometrical shapes formed by connecting. Now this is very important. Now previously, now I explained. I think wave pulse. Considering wave front, it must be credited as wave pulse, not wave front. Now only we are learning about what is this wave front. Put your topic wave fronts, then write down geometrical shapes formed by connecting points. Write down geometrical shapes formed by connecting points in the same phase are called wave fronts. Geometrical shapes formed by connecting points in the same phase are called wave paths. Are called wave fronts. Are called wave fronts. I will explain. Don't worry. Write down the point. Now, example. Example. Write down. Wave fronts produced on a water surface. Wave fronts produced on a water surface by a point vibrating source. By a point vibrating source are circular. Now, first of all, you should understand now. Now, you guys have an understanding about wave pulse, but still you don't know what does it mean by a wave front. That's very important to understand. Now, look at when you look at here, right? Just look at here. Now, just think about now there is a water vessel. That vessel is completely filled with water. If you have a point vibrating source, very small, very tiny, small point vibrating source, what you do, you dip that point vibrating source on the surface of the water. When that point vibrating source vibrates continuously, you know what would happen? From the point of vibration, away from the point of vibration, there will be water waves propagate. There will be water waves propagating. Okay? Then you might have seen that, you might have seen some sort of circular shaped geometries move away from the point of vibration. You might have observed that type of thing, right? Those are we call as wave fronts. Okay, look at it. Now, now I will consider side wave. Then later on, I will do the top wave of that water wave propagation. First of all, I will do the side wave and I will explain how these wave fronts are obtained, how these wave fronts are drawn. Look at here. This is your water surface, right? This will be your water surface. In that case, now just think that now a point vibe now side wave. This is my side wave. So then let's say now here is my point of vibration. then you will observe that water waves are propagating away from the point of vibration, right? When someone is looking from this side, it appears in this way. It appears in this way. Am I correct? So then we know that these points are crests. Then these points are troughs. Then we know that now. How we define wave fronts? Wave fronts means when you connect the points which are under same phase, the geometrical shapes obtained, we call those geometrical shapes as wave fronts. When you connect the points which are under same phase, then the resulting geometrical shapes we call as wave fronts. Then we know that these points, now here I only have drawn the side view, but you know that when one looks from the top, then you know when one looks from the top, then you know when one looks from the top, so you also draw with me, right? Right. Then we know when one looks from the top, now here is our point of vibration. Here is our point of vibration. Okay. Let's say here is our point of vibration. Then what would happen? This water waves propagating in all the directions. This water waves propagating in all the directions. Do you understand what I'm saying? These water waves propagating in all the directions. Right. This is the top view. Okay. This will be the top view. This is the top view. So then if you connect, now we know these points, these are crests, these are crests. We know crests have same face. We know these are troughs. We know troughs have same face. Then we know that. If I mark, look at it. Now look at it. Now these are crests. These are crests in the wave. Waves propagating from the point of vibration. If I mark all the crests, if I need, these are crests. If I connect all the crests by lines, That geometrical shape, this is what we call as that circular. If I connect all the crests together, then I am getting some sort of circular shape geometry. That circular shape geometry we call as wavefronts. Do you understand? Then if I properly mark the wavefronts, so you will be able to obtain circular shape wavefronts. Then you'll be able to obtain this type of wavefronts. Look at it. Circular shape. Now this is your trough. If we mark the trough, now crest and this is crest. Here is your crest. Here is our crest. Look at it. Then if we connect all the crests together, just think about this one and this one. There will be circular shape geometries. Those circular shape geometries we call as wavefronts, circular wavefronts. We call as circular wavefronts. Okay. Then if I connect them, so then we are getting circular shape wavefronts. Circular shape wavefronts. Right, circular shape wavefronts. Right. And if you mark the troughs together, somehow there should be a trough like so. There's a small mistake in this diagram. In here, there must be something. There must be a trough, and then only there will be a crest. You got it? A small mistake. Should be in this way. Right. Then when we mark all the troughs, all these troughs, so there will be circular shape geometries. If I connect all the trough points together, there will be a circular shape geometry. Circular shape geometry. Right. If I mark all the crests together, there will be a circular shape geometry. I mark in dark color. Right. Then if I mark again all the troughs together, if I mark all the troughs together, there will be circular shape geometry. You got it? You got it. Then if we mark again all the crest together, then we are getting circular shape geometry. We equal them as wave fronts. Then these wave fronts are, you can clearly see, circular shape wave fronts. I hope that you can understand what I'm saying. Then I think you will understand. These circular shape wave fronts are propagating away from the point of vibration. These wave fronts are propagating away from the point of vibration. You understand? Quickly draw this diagram. Draw it quickly. Draw it quickly. Right. So then that is done. Now, right. Now, first example was when we vibrate by using a point vibrating source on the surface of the water, we realize that. So there will be circular shaped wave fronts formed and they propagate from the center of oscillation to center of vibration to away from the center. So you understood what is this wave fronts. Wave fronts mean simply when you connect the points which are under same phase. Then the geometrical shift that you obtain, that's what we call as wave fronts. Then first example, what, circular shape wave fronts. The example number 2, write down. Wave fronts generated by a point, light if not sound. Write down second example. Wave fronts generated by a point, light or sound source are spherical. Now here we vibrate the surface of the water. Therefore we obtain circular shape wave fronts. But just think, if you take a point vibrating source in the air, if you take a point vibrating source in the air, and if that vibrating source is vibrating, then what type of wave fronts producing? Some sort of spherical wave fronts, spherical wave fronts. So draw this diagram. This is the source of sound. Point vibrating source of sound. That sound is distributing to all the areas. Now we can't draw spheres in a 2D board. Now it's a 2D whiteboard. Then we can't draw 3 drawings properly. Now you should understand, it seems like circular wave fronts, but it's not circular wave fronts. These are spherical wave fronts. This is vibrating source, spherical wave fronts. Spherical wave fronts. Right. The next example, number 3, wave fronts produced by a straight rod on water surface are linear. Now, depends on the vibrating source, understand there can be circular shape wave fronts. If not, there can be spherical wave fronts. If not, there can be linear wave fronts. Just think there's a surface of water. And if you have a rod, now you have, let's say you have a rod, straight rod. Now what you just think about, take this marker. It seems like a straight rod. Now you have a very nice water surface. Then what you do, you barely dip. You just dip this marker on the surface of the water, and when you vibrate it, what type of wave fronts that you will be appear? You will appear straight line wave fronts. In example number 3, write down wave fronts produced by a straight rod on water surface are linear. right? In that case, mm, in this case, now here, look at it. Now if I draw some sort of 3D diagram, now we are having a rod in this way, the straight rod, a straight rod, right? Now initially, this was your water surface. See your water surface. Then when this rod is vibrated, what would happen to the water? This water is also produced now. When this rod is vibrating up and down, this rod is vibrating up and down. As a result, what will happen? As a result, what will happen? You will observe that. You will observe there will be water waves producing. Water waves producing. Right. Then water waves propagating in that way. The water waves. Then the water waves producing. Right. Then when we connect all the crest points together, what type of geometry that we obtain? Straight line. When we connect all the crest points together, what type of geometry will obtain? Straight line. When we connect all the trough points together, geometry line is straight line. So therefore, what would happen when we vibrate the water surface by using a rod, straight rod? The wave fronts that we obtain are linear, straight line wave fronts. Do you understand? That's the important thing I wanted to highlight. So then, if I draw a 2D diagram, this is my rod, top wave. This is my rod. It's my rod. Then what can we say about the water wave fronts? The water wave fronts. Now here, then we draw these diagrams. Okay, now this is what crest. If I connect all the crest points together, this is the water wave fronts produced due to crest. Okay. And this one, So these dark lines are the water wave fronts produced due to the crests. These water wave fronts produced due to the trough. You understand? Right. Then last point regarding put your topic race. Now race means lines perpendicular to the wave fronts. Now race means the lines perpendicular to the wave fronts. Look at it. Now these are the wave fronts. Then if we draw perpendicular lines, so we call they show the direction of wave front because these wave fronts are propagating forward direction. Lines perpendicular to the wave front we call as rays. These are rays, right? So then if it is circular wave fronts, if it is circular wave fronts, lines perpendicular to wave fronts, see, perpendicular. Lines perpendicular to the wave fronts. They are called as wave rays. They are called as rays. Right. Okay. So then I think first section is completely finished. The transverse waves and longitudinal waves, that idea is entirely finished. Now we'll compare transverse waves and longitudinal waves. Just take your book, CR book, full page CR book, divide your page into two. Fold your page, take one paper, fold your page into two. One side write down transverse wave, right side write down longitudinal waves. And we are going to compare them, right? We are going to compare them. Now in transverse side, write down. In transverse side, write down. In transverse side, write down. Number one, moves by propagating energy. In longitudinal side also write down, moves by propagating energy. Next point, in transverse side, satisfies V equals F lambda. In longitudinal side, satisfies V equals F lambda. Next point, in transverse side, waves propagate perpendicular to the oscillation. Waves propagate perpendicular to the oscillation. In longitudinal side, write down, wave propagates parallel to the oscillation. Next point, in transverse side, it has troughs and crests. It has troughs and crests. In longitudinal side, write down, it has compressions and rarefactions. Next point, in the transverse side, write down, phase difference between two consecutive crests 360. It's very important point, right? When you consider two crests, two adjacent crests, phase difference between, write down, phase difference between two consecutive crests is 360, inside the bracket 25, and the gap is lambda, wavelength. In a transverse wave, when you consider, now very important idea, in a transverse wave, when you consider two, just take about two crests adjacent, then both of them are in same phase, their phase difference is 25, that means 360 degree, and the gap is lambda wavelength. In longitudinal side, write down, phase difference between two consecutive compressions is 360, inside the bracket 25, close the bracket, and the gap between them is wavelength, right? Then next point, in the transverse side, phase difference between two adjacent crest and trough is 180. Phase difference between two adjacent crest and trough is 180. Inside the bracket 5. Close the bracket, and the gap between them is half the wavelength. And the gap between them is half the wavelength. Lambda over 2. Now in the longitudinal side, write down phase difference between two adjacent compression and rarefaction is phase difference between adjacent compressions and rarefaction. Write down phase difference between two adjacent compressions or rarefactions is, okay, my bad. Okay, now correct in this way. Phase difference between two adjacent compression and rarefaction is 180 degree inside the bracket 5, and the gap between them is half the wavelength. And the gap between them is half the wavelength. Lambda over 2. Next point, in the transverse side, particles of the medium at the positions of the crests and troughs are at instantaneous rest. Particles of the medium at the positions of crests and troughs are at instantaneous rest. In the longitudinal side, write down particles at of the medium. Particles of the medium at the positions of compression and rarefactions are at instantaneous rest. Particles of the medium at the positions of compression and rarefactions are at instantaneous rest. Then next point, the direction of, in the transverse side, the direction of medium particles present in a crest and trough opposite to each other. The direction of medium particles present in a crest and trough opposite to each other. In longitudinal side, write down there is no displacement of medium particles in a compression and rarefaction. There is no displacement of medium particles in a compression or rarefaction. Then next point, write down in the transverse side, there is no difference in pressure and densities of the particles in the medium at crest and trough. Write down there is no difference in pressure and densities of the particles in the medium at crest and troughs. In the longitudinal side, write down medium particles are subjected to maximum pressure during compression, and medium particles are subjected to minimum pressure during maximum rarefactions. And write down in the longitudinal side, medium particles are subjected to density during, sorry, okay, in this way, medium particles are subjected to maximum density during compression, minimum density during rarefaction. Then that section is entirely finished. Then the section is entirely finished. Now we want to look back about, we want to think now that section is completely finished. Now we are focusing about properties of waves. Now this is also one of the very important section. Properties of waves, that's very important section. Then if we can finish this section quickly, then we can go to Doppler effect, then we'll go back to standing waves, right? So now you put your main topic, properties of waves. Put your main topic, properties of waves, right? Give me a second. Right. Now we are talking about properties of waves, right? Properties of waves, right? Okay. Now, when talking about waves, waves have different characteristics, that means different properties. But the most now, I think in all levels also you learn that there are some important properties, if not characteristics, reflection. So no matter it's a water wave or sound wave or any kind of wave, if it is a wave, it must show reflection. Reflection is one of the main characteristic of a wave. If water waves is a wave, that must obviously show reflection. Then likewise, what are the other properties of waves, other characteristics of waves? Number one, reflection. Number two, refraction. See, you learn this reflection and refraction in your O levels, I think. In addition to reflection and refraction, there are other properties. Diffraction, reflection, refraction, diffraction. Then fourth one is interference. Fifth one will be polarization. So in this section, we learn about reflection, but refraction is much. We learn more about refraction and reflection. Diffraction, interference is somewhat critical section. The last one is polarization. We don't talk so much about polarization. We explain and we finish it, right? Okay. So then put your topic properties of waves. Number one, properties of waves. Number one, reflection. Number one, reflection. Number one, reflection. Reflection. Properties of waves. Number two, refraction. Number three, diffraction. Number four, interference. Number four, interference. And number five, polarization. Number five, polarization. Right. First, we'll talk about now this reflections. Very important. Now, obviously, we talk so much now. In now, after this chapter completes, now at the end in Unit 3, we have to learn about light optics. In optics, we will learn more about refraction. Optics section is entirely about refraction. Okay. Now, reflection and remaining properties of waves, diffraction, interference, polarization. We don't learn so much. Mainly, we focus in refraction. Optics completely about refraction. Okay, it's a very good section. Now, put your main topic reflection. Now, we'll define what is this reflection. Take your red color pen and write down. Take your red color pen and write down. Take your red color pen and write down. Give me a second. Right. Now, take your red color pen and write down the definition of reflection. Now, already you know that. What is reflection? No matter this characteristic is valid for any type of wave. It can be water waves, sound waves, if not transverse wave in rope. Even electromagnetic waves, this reflection characteristic is common. Since all they are waves, they must show phenomena called reflection. Now, reflection means basically what happens in a when a wave propagating in one medium, when wave propagating in one medium, when that wave hits a surface, when wave propagating in one medium hit the surface, as soon as it hits the surface, it will come back to the same medium. Do you understand? If not, we can say in the at the common interface, that means some sort of thing which separates the mediums. When a wave propagating in a particular medium, after incident at the common interface, if that wave come back to its original medium, this wave is coming in this way. After incident at the common interface, if the wave come back to the original medium, that means initial medium, then we call that phenomena as reflection. Write down the red color pen. Red color pen. The phenomenon that a wave traveling in a medium. The phenomenon that a wave traveling in a medium hitting a surface that separates the medium and hitting a surface that separating a medium and returning to original medium. Returning to original medium. Returning to original medium. Look at it. Now, very carefully listen. Now this will be the common interface which separates my two mediums, right? It's my common interface. Common interface. Common interface. Then we know now above this common interface, medium 1 is there. Medium 1, it can be air. Medium 2 can be water. Any type of two mediums. Medium 1 is my second medium. Medium 2. So let's say now there is a wave. That wave is propagating in medium 1. That wave is propagating through medium 1. So we call that wave as incident wave, right? This wave we call as incident wave. Incident wave. Then what happened? Now reflection means as soon as incident wave incident at the common interface, it will go back to, if it will come back to the original medium again. This wave was propagating in medium 1. As soon as incident at the common interface, this wave will be move back to the original medium, same medium. Rather than get into the second medium, after incident wave hit the common interface, it will go back to the original medium. We call this phenomenon as reflection. Then we call this wave reflected wave. Reflected wave. I think you understood. Reflected wave. Right. Right. Important. Now you should understand in a reflection. Do you think, just think about now, wavelength of the incident wave. I say lambda I, wavelength of this incident wave is lambda I. And I say frequency of the incident wave is Fi. And I say velocity of the incident wave is Vi. Understand, after reflection, just take about this reflected wave. Its wavelength is lambda. R, frequency FR, velocity of the reflected wave is VR. If it's a reflection, very important thing, understand, if there's a reflection, there is no difference in frequencies, wavelengths, and velocities of incident wave and reflected wave. Do you understand? Whatever the velocity of incident wave is same as the velocity of reflected wave. Whatever the frequency of incident wave is same as the frequency of reflected wave. Whatever the wavelength of the incident wave is same as the reflected wave. So therefore understand, both of them have same lambda, same V, same F. Red color important. Important. The wavelength, comma, velocity and frequency remain unchanged in a reflection. The wavelength, velocity and frequency remain unchanged in a reflection. The Vi means it's VR. Lambda I means lambda R, no difference. Fi means Fr. Again, but this type of thing could occur. This type of thing could occur. Now, just think that now, when there is a car, if that car is traveling with a big speed, suddenly when this car collide with the wall, what would happen? Its energy will be dissipated, right? Now there's a car, that car is propagating, this car is traveling with a velocity, suddenly it hits a small rock. Just think now, what happens now? There is some sort of bump. In a highway, let's say there's a bump, that car is traveling with a big velocity. Let's say kinetic energy. Energy belongs to that car is 1000 joules. When that car is traveling and when the car hits the bumper, still the car is moving. But due to the bumper, what would happen? Just before hitting the bumper, energy of the car was 1000 joules. After collide with the bumper, still your car is moving, but kinetic energy, the energy of the car is 900 joules. Did you understand? What happened? There is some sort of reduction in energy. Very similar manner, when you consider incident wave and reflected wave, very carefully listen. When you consider incident wave and reflected wave, energy of the incident wave is always larger than energy of the reflected wave. Do you understand? Energy of the incident wave is larger than energy of the reflected wave. That's very important thing. Now, which parameter now in a wave? In a wave, which parameter measures the energy of the wave? Energy of a wave is measured by the amplitude. The larger the amplitude of the wave, larger the energy carried by the wave. Do you understand? Energy carried by a wave is measured by that wave's amplitude. If a wave has large amplitude, write down your note, okay? Write down. Amplitude is a measurement of the energy carried by the wave. Write down. Amplitude is a measurement of the energy carried by the wave. If amplitude is large, energy carried by the wave is large. If amplitude is smaller, energy carried by the wave is smaller, right? Then, now what happens now? When you consider incident wave and reflected wave, incident wave, because this incident wave carries, let's say 500 joules of energy. Now somehow this incident wave collide with the interface. So therefore what would happen? There is a small reduction in reflected wave energy. If you consider energy of incident wave is 1000 joule, energy of reflected wave will be 900 joule. Then what would happen for the amplitude? I told you, amplitude is a measurement of energy. Larger energy means larger amplitude. Smaller energy means smaller amplitude. Then what happens? This one is having incident wave carries large energy, therefore its amplitude is large. Reflected wave carries small energy, therefore its amplitude is somewhat small, not fully small, somewhat small. But there is no change in lambda f and v. There is no change, same, but small reduction in the amplitude of reflected wave. Write down amplitude of reflected wave. Amplitude of reflected wave decreases in all other reflections. Amplitude of reflected wave decreases in all other reflections except total internal reflection. Except total internal reflection. Please highlight total internal reflection. Now you don't know what is this total internal reflection. When we learn optics, when you learn optics, I teach you what is this total internal reflection, right? And that idea is also done, right? Then topic reflection of water waves. Topic reflection of water waves. Main topic reflection of water waves. Subtopic reflection of straight water wave fronts. Subtopic reflections of straight water wave fronts. Reflection of straight water wave fronts. Right? Okay, now draw this diagram with me. Now, can you remember now? You know how these water wave fronts and rays. Now, you know, basically rays show the direction of wave fronts. Wave fronts means when we connect points which are in same phase, that geometrical shapes we call wave fronts. Now we are going to understand the reflection of water waves by drawing water wave fronts and the rays. Do you understand? Then topic is reflection of straight water wave fronts, and draw this diagram with me. Right. Draw this diagram with me. Now this is the water ray. It's a ray, right? Then we know wave fronts perpendicular to ray. Wave fronts perpendicular to ray. If I draw the water wave fronts, if I draw them, if I draw them, right? My water wave fronts, straight water wave fronts, straight. These are my water wave fronts. Now these are straight linear water wave fronts. They are propagating towards the common interface, right? What can you say about the distance between two consecutive water wave fronts? Can you remember how we define wave front, how we define wavelength by using wave fronts? The distance between two adjacent wave fronts we call as two adjacent wave fronts in same phase, okay? The distance between two adjacent wave fronts in same phase we call as wavelength lambda. Then the gap between them is gap between wave fronts, it's lambda. Lambda. Gap between them is lambda. Lambda. Right. So we call these wave fronts as right. Can you hear me? Right. So we call these wave fronts as incident wave fronts. We call them as incident wave fronts. Right? We call them as incident wave fronts. These are incident wave fronts. Incident wave fronts. Incident wave fronts. Then what we call for this one? Incident ray. So this one is incident ray. Incident ray. Right? So then what happens? Now reflection. Now this is we call as understand. This is we call as this is the point capital O. This point capital E. This point capital O, incident point. We say point capital O as incident point. This point capital O is called as incident point. Incident point. Incident point. Right? Then point ON, this line, normal drawn to the common interface. This ON is the normal, perpendicular line drawn to the common interface. ON means normal drawn to the common interface. Right. Then what is this, sir? I say this one is my common interface. This one will be my common interface. Common interface. Right. Then when I draw reflected ray, now this is my incident ray. If I draw my reflected ray will be this way. Reflected ray would be this way. The straight line, I will draw somewhat inclined. But we know that now. Incident wave and reflected wave, there is no change in wavelength. Whatever the wavelength between two adjacent wave fronts on the same phase, lambda, same wave front will be the two adjacent wave fronts, reflected wave fronts, which are in same phase. If I draw my reflected wave fronts, it will be this way. These are my reflected wave fronts. Reflected wave fronts. These are my reflected wave fronts. So what can you say about the gap between two adjacent wave fronts which are in same phase? Lambda, 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 lambda. So we call these wave as reflected wave fronts. Reflected wave fronts. Right? Then what about this one? Reflected ray. This one will be the reflected ray. Reflected ray. Okay. Now I mark incident angle. Look at here. Now this one is my incident ray. This one is my normal. The angle between incident ray and normal is incident angle I. The angle between the angle between reflected ray and the normal is refracted angle R. Now mark down what is this I and what is R. I means incident angle, R means reflected angle. Reflected angle. And now we'll write down the laws of reflection. Laws of reflection. Write down. Now, first law of reflection. Write down. Incident ray, comma, reflected ray, and the normal drawn at the incident point. Incident ray, comma, reflected ray, and the normal drawn at the incident point are in the same plane. Now, this incident ray, this one, reflected ray, this one, and the normal, all must be in the same plane. You got it? They must be the same plane. Let's say this blue color one is your normal. Sorry, yeah, red color one is your incident. Black one is your reflected ray. They all must be in the same plane. Second point, incident angle must be equal to reflected angle. I equals R In reflection, always understand incident angle exactly equal to deflected angle. I equals R, right? So then now currently we are talking about first characteristic of, if not first properties of waves, that is reflection. That is reflection. In reflection, now we know what is the idea. If the wave which are moving in a medium after incident on a common interface, if the wave come back to the original medium, we call that phenomena as reflection. In reflection, velocity, frequency, and wavelength of incident wave and reflected wave won't change; they remain same. But due to the reflection, what happens? Energy carried by the reflected wave has reduced. As a result, amplitude of reflected wave is reduced. Then loss of reflection means incident ray, reflected ray, and this normal must be in the same plane. Always incident angle equals to reflected angle. Then we talked about water wave reflection. And also now we are talking about reflection in transverse waves in ropes. Put to your next topic. Put to your next topic. Reflection of transverse waves in strings. Reflection of transverse waves in strings. That is our next point. Right? Right. Then we'll stop from here now. Tuesday morning, I will keep another additional class Tuesday morning. So then, because my target is somehow bring both physical class and online class speeds in same speed. Tuesday morning also we'll keep another class. Then Wednesday we have a class. Then we can come to same speed. Okay. Then I'll stop from here. Right.